You know, underneath our cities, right beneath the parks and parking lots we walk on every single day, there's actually a hidden chemical history. Welcome to This Explainer. Today, we're uncovering the massive, often totally invisible engineering efforts required to rescue heavily polluted lands and protect our groundwater. When we look at a seemingly normal patch of dirt, we rarely think about the complex, sometimes toxic legacy buried just beneath our feet. Well, today, we're going to peel back those layers.
So we constantly hear about protecting human and ecological health, right? But what actually drives the incredible multi-billion-dollar effort to rescue and reuse degraded, polluted brownfields instead of just, packing up and building somewhere else? I mean, why not just fence off the bad areas and develop on beautiful, untouched, pristine lands? Well, as we're going to see, the answer is deeply tied to our survival, our economics, and our absolute responsibility to the future.
The sheer visual reality of this problem is honestly staggering. Just look at the historic gasworks site and that striking neon green pump sump. I mean, that almost glowing green water perfectly illustrates the severity of the chemical footprints we leave behind. In this case, we're looking at heavy contamination with nickel, zinc, and copper. We aren't just talking about a little spilled oil here, we're dealing with intense, localized toxic hazards. Heavy metals like these, they don't just disappear. They persist in the environment, poison the soil, and actively seep right into the very water systems we rely on to drink and grow our food.
Several billion euros. That is an astronomical financial commitment spent every single year in the European Union alone, just to heal the land. And because the costs are so remarkably high, it's an absolute necessity that this money is spent wisely on truly sustainable solutions, rather than just slapping on temporary band-aids. We really need rigorous, science-backed strategies to make sure we actually fix the root of the problem and don't just throw endless money into a toxic pit.
To understand how scientists and engineers actually pull this off, our agenda today is pretty straightforward. First, we'll look at why we rescue polluted land. Then, breaking the pollutant linkage, diagnosing the contaminated site, and finally, digging up solutions.
Let's kick things off with Section 1, Why Rescue Polluted Land? Here we'll look at the philosophy of sustainability and environmental protection.
The bedrock of this whole effort is sustainability. This is a concept that really took the global stage back at the 1992 UN Earth Summit in Rio de Janeiro. The goal here isn't just cleaning up dirt, It's about conserving our precious land resources. By reusing contaminated land, we massively decrease the pressure to develop greenfield sites, those pristine, untouched natural areas. We're actively fighting against endless urban sprawl, which otherwise just paves right over critical wildlife habitats, increases commuting emissions, and wrecks natural ecosystems just to build the next shopping center.
And this brings up a really fascinating tension in remediation. It's a hugely complex balancing act. When deciding to clean up a site, we actually have to weigh the immediate negative impacts, like the heavy traffic from trucks moving soil, the noise, the dust, and the greenhouse gas emissions, against the incredible long-term positives. We're talking about fully restored ecosystems, vastly improved soil fertility, and a renewed landscape value. Essentially, we take a coordinated short-term hit for a permanent environmental victory.
Moving right along to Section 2, Breaking the Pollutant Linkage. This is all about controlling the risk of contamination.
So the absolutely crucial point here is that pollution is only a real risk if the chain connects the contaminant to a vulnerable target. We call this the pollutant linkage, and it means we can manage the risk by attacking the chain at 3 distinct points. Think of it kind of like a dangerous forest fire. Number 1, we can modify the source directly, which is like putting out the fire itself, maybe using in situ bioremediation to destroy the chemicals. Number 2, we can break the pathway. This is like building a massive fire break, say constructing a physical barrier so the pollution simply can't travel through the groundwater. Or number 3, we can modify exposure to the receptor. This is basically the equivalent of evacuating the town, limiting access to the area so humans or wildlife are kept entirely out of reach. Break just one of these 3 links, and the immediate risk collapses.
Now, stepping on to the environmental crime scene with Section 3, Diagnosing the Contaminated Site. This is the real environmental detective work.
Before anyone even thinks about picking up a shovel, investigators follow a super strict protocol. It kicks off with a simple walk-over survey, literally just looking for visual clues on the surface, like poor drainage, unexpected land subsidence, or the ruins of old foundations. From there, they escalate to a detailed site investigation, taking specific soil and water samples. They need to figure out exactly how the water is moving underground to know how fast a poison might be spreading. After that, remedial treatment criteria are determined based entirely on what the land will be used for in the future. If a site is going to become a children's playground, it needs an extraordinarily thorough cleanup. But if it's just becoming an industrial parking lot capped with concrete, the criteria might be a bit different. Finally, they set up long-term monitoring to make absolutely sure the site stays safe for decades to come. Knowing who we're looking for helps us build a suspect list. On one side, we have VOCs, or volatile organic compounds. These are nasty organic compounds like benzene that evaporate super easily into the air, creating serious vapor hazards. If you've ever caught that sharp whiff of fumes at a gas station, you've met VOCs. On the flip side, we have the stubbornly difficult NaPLs. These are non-aqueous phase liquids, mostly petroleum hydrocarbons, and they absolutely refuse to mix with water. Think of how oil and vinegar separate in a salad dressing, right? No matter how hard you shake it, the oil separates out. That's exactly what these chemicals do underground, which makes them incredibly tricky to flush out. To get even more specific, those NaPLs come in two distinct, highly problematic flavors. First, we have L-naples, which are light. Because their density is less than 1, they literally float right on top of the groundwater, kind of like an oil slick on a puddle. Then we have D-naples, which are dense. These guys are heavier than water, meaning they sink deep, deep down into the aquifers. Because they sink so deep and pool into tiny microscopic cracks in the bedrock, D-naples are an absolute nightmare for investigators. They're incredibly elusive, literally like trying to clean thick oil out of a deeply porous sponge 100 feet underground. Whether a chemical floats or sinks completely changes the whole investigative approach required to track it down.
Finally, that brings us to Section 4, Digging Up Solutions. This is all about engineering the cleanup.
Engineers face a massive choice right out of the gate. They can either treat the soil exactly where it lies, a process known as in situ treatment, or they can physically dig it up, which is ex situ treatment. Now, treating the soil in place is definitely an option, but it usually takes way longer because you're relying on slow, natural processes. So engineers often turn to ex situ treatments. That's where they bring in the heavy machinery and completely excavate the dirt. Sure, ex situ costs more, requires super careful material handling, and kicks up a lot of dust. But it gives you a much faster and significantly more uniform cleanup because the soil can be continuously screened, tracked, and mechanically mixed.
Once that contaminated soil is actually out of the ground, engineers can deploy literal biological armies to eat the pollution. They do this through techniques like biopiles, where the dirt is heaped up and aerated with specialized piping to keep the oxygen flowing. They also use composting. By mixing the toxic soil with bulking agents like wood chips and manure, they perfectly balance the carbon and nitrogen. Essentially, they're setting up an all-you-can-eat buffet to feed a microscopic cleanup crew of bacteria, supercharging their ability to consume the pollution. Or they might use land farming, where the soil is spread into lined beds and periodically tilled, exactly like an agricultural field, to promote continuous natural degradation.
But, what if biology just isn't aggressive enough for the job? If the compounds are highly toxic or incredibly stubborn, they have to bring out the big guns. They can blast the soil with extreme thermal treatments. We're talking hot gas, incineration, or thermal desorption, which uses intense heat to literally vaporize the chemicals right out of the dirt so they can be captured. Alternatively, they can use chemical extraction, running the soil through a system where an extractant is used to physically dissolve and wash those stubborn pollutants right out of the earth. Knowing all of this, we have to look at the big picture. The absolute gold standard for these massive cleanups is the reduction of aftercare. We want to implement sustainable solutions that require no endless mechanical pumping and no endless human control. So, as we look at these incredible engineering feats, we have to ask ourselves a pretty provocative question. Are the environmental solutions we design today truly fixing the problem permanently? Or are we just managing it for tomorrow and quietly leaving the risk for the next generation to handle? It's something every environmental engineer, and really, every single one of us who relies on clean land and water, needs to think about. Thanks for joining me on this explainer, and keep questioning the ground beneath your feet.